Hello, so today we're talking about the chain rule, which is the most important rule of differentiation. By that, I mean that you will be using this all the time, and it is something that you need to be very comfortable doing quickly and avoid errors. So as a start, let's review some notation. We know what this thing says. It says that we want to find how the function sine of x changes when x changes, when we increase x. And we already know that it changes just like cosine of x. That cosine of x describes the change. But what if I was to ask the same question? So how does something change with respect to x? But this time I would be asking this about the function sine of theta. Would this make sense? Well, not really, because the function is not a function of x. This expression involves theta as the argument. And if the only thing this depends on, the value of this expression, is theta, then it does not change with x at all, and the value would be 0. But would it always be the case? Well, this depends, because if theta is actually a function of x, in other words, if the change in x makes theta change in some manner, then the whole expression sine of theta would change with x as well. So now it makes more sense to ask how this whole expression changes as x changes. Because change in x makes theta change because theta is a function of x. And in turn, this whole thing, when the value of theta changes, the value of sine of theta changes. And the chain rule helps us deal with these exact scenarios. So what is this going to be equal to? And we'll answer this in this video. But first, a few quick points about notation again. So please remember this, even though it might sound trivial. Keep this in mind all the time. If I ask, how does this expression change with respect to apple, then and only then does it change as cosine of apple. If this thing inside is not what we're differentiating with respect to, cos of apple cannot be the derivative, or cos of apple alone cannot be the derivative. So this is one thing. And just one more. This notation with the prime, you already remember this, but just again, to be specific, it refers to a derivative with respect to the argument that you have here written in these brackets. In other words, this means that I'm doing d by dx of function f. Okay? I could include these brackets here, but I don't need to. I could just write this. So if I had a function that takes in the value of g, and the function's name is h, then h prime would mean nothing but the answer to the question, how does h change as g changes, the value of g changes. And even though this notation doesn't explicitly tell us as much as this one, it'll be worth using as a shorthand. So we're ready to discuss the chain rule. And to be a bit more formal, we'll use this to differentiate composite functions. So situations when we have a function inside of another function. You should be familiar with the idea of composite functions. If not, make sure you revise that before continuing with this video. And we have already seen an example of a composite function. I showed you in one of the previous videos a large function that I promised we were going to differentiate at some point. And this one was a function of sine of another function of x, and the inside function was x squared minus 3x plus 1, a quadratic. So we could say that we had an outer function f, which was sine of x, and the inside function g, which was x squared minus 3x plus 1. Here comes the important part, so focus and look closely. If I were to treat this function, let's call it big F, as a function of this whole expression, call it g, I could write that df over dg, so how the big F function, this expression, changes with respect to its argument, so this whole expression, is basically going to be cosine of g. But if I want to go a step further, and ask how this changes with respect to x, I need to first think about how the change in the value of x impacts the value of g, and then how the change in the value of g impacts that of function f. And there's quite an easy way to understand what we would need to do in this case. Think about if a train goes 2 times as fast as a car, and the car goes 3 times as fast as a bicycle, how much faster does the train go than the bike? Well, it's pretty obvious, right? But how would we calculate this? We would do 2 times 3, and we would get 6. And essentially speaking, this is what the chain rule is about. So again, I'm asking, how does the big F function, this whole expression, change when the argument of function g changes, when x changes? First, I would need to think about how the function f changes with respect to g. So how does the change in the value of this whole expression, say by 1 unit, impact the value of f? And then look at the second step and multiply by how the function g, the value of the function g, changes with respect to x. And this is the whole idea of the chain rule. And in fact, there's even more ways to remember this formula. Because you technically could even think about these guys cancelling out and the function g being sort of a bridge between f and x, which would disappear if we were to treat these as fractions and give us the f by dx. But be careful with this. This is not what's actually happening, although the truth isn't much more difficult. So here I wrote an alternative way of writing the same statement, except I used the fact that we technically could look at the function big F as a function of x, because it's a function of g, which is a function of x, so sort of indirectly. And because I'm differentiated with respect to x, that's what I'm interested in. But in order to perform the differentiation, we needed to go through these two functions. We needed to split the function big F into these two functions, use them to create a composite function, and then this notation basically is the prime notation instead of the so-called Leibniz notation, so with small d's. But pause and make sure you see how these statements are indeed equivalent. And when you look at the formula booklet, here we have the same thing, except they're a bit more formal, a bit more pedantic with the symbols, so that's why they're explaining here what y and u means, so that it is justified for them to not have to write arguments here every time. Because technically one could say that this should be written here to state explicitly functions of what we're treating these letters as, except I removed it for clarity. The point is, the formula booklet gives it to you in some way equivalent to the ones we've discussed, but the goal is that with practice, you get to feel how to apply it, so we don't even need to look the formula up. So that's what we're going to do now. Look at some examples. In the very beginning, I told you that the crucial bit about all this is actually being able to apply this quickly and without errors. And honestly, one could even learn the chain rule without understanding what happens behind the scenes, just by practicing, looking at examples, and getting to feel the patterns. Because what happens algebraically isn't actually too complicated, it's kind of repetitive. So I want to find the derivative of this expression. I brought our summary of standard derivatives here. So let's first identify what composition of functions this expression is. Because we already know how to differentiate some simple functions, and the standard derivatives of those is what we have in the formula booklet. But now what we can think of the outer function is bringing e to some power x, exponential. Its derivative will indeed be just e to the power of x. The same thing, nothing changes. And the inner function is what we're putting into the exponent. It's what we're putting into the function f. And it's not just pure x, it's actually a function of x. Let's call it g. Technically speaking, it's a polynomial, first order polynomial, first degree. So we know how to differentiate it. We know its derivative would basically be just 2. Yeah, we're either using this rule, this formula, or common sense. If this is the equation of a line, then here stands the gradient, and the line has the constant gradient of 2. So now, first, I'm saying that this whole function changes with respect to this argument like this, stays the same. E to the power of this argument stays. That's the first part of the chain rule. And now I need to multiply by how the inner function changes with respect to x, already x itself, which equals to 2. And this would be the second bit of the chain rule. And obviously I can rewrite it in a simpler and a nicer form. So pause to make sure which bit corresponds to which of these two parts. First we were differentiating this whole expression with respect to this shape, this apple, this whatever. And the way we differentiate such exponentials is basically we'll leave it as it is. And so we did. That was the differentiation of our outer function. And then we did the second bit. We multiplied by how g, the value of the inner function, changes with respect to x. And that was just 2. So we multiplied by 2. And that's the result. So let's go to the next example. Here we will use this first standard derivative and of course our chain rule. So let's identify the outer function first. This is bringing something to the power of 3. How do we differentiate this? How do we differentiate x to the power of 3? Well, we bring the 3 to the front and decrease the exponent on the whole thing by 1. So now it's to the power of 2. And that's the first bit of our chain rule formula. Now we need the second, so how the inner function changes with respect to x. So now we're just differentiating this polynomial, well, it's not a polynomial, this series of powers with respect to x. And this is going to be our second part of the chain rule formula. So 5 times 3 is 15, x to the power of 1 less than 5 is 4, and then minus, notice that root x is nothing but x to the power of a half. So I have minus a half x to the power of a half minus 1, which is negative a half here. Yeah, and these brackets are here, the second bit of the chain rule, the derivative of the inner function, while this was the derivative of the outer function. And this can go on and on. If we have a function of a function inside a function and so on and so forth, we would just multiply those corresponding derivatives one by another until we reach this smallest argument that's the most inside and that we're interested in. I'll leave some examples with the solutions so that you can see this, but also loads of examples to practice the chain rule as a whole.